Welcome back. This is lecture 57. We just had a long break, Thanksgiving break, so we are back and fat and maybe not so happy, but I just returned test 4 and they were not delightful, so we're in a little bit of mourning here this morning. We're going to finish up 5.7, trig substitution. I'm actually kind of shocked when I look in the book. It has less there than I thought it did, and I thought it was kind of sparse before I glanced at it again this morning. So we'll try to embellish what is in the book a little bit, and there are some problems, some good problems at the end of the section. I'm not sure actually how many of those made it to WebAssign, so I'll recommend some problems using trig substitution for you to look at. So 5.7, this is actually on page 401. This is one of the reasons why it's taken us probably more than a week to cover this section, because there are trig integrals, sines and cosines, secants and tangents. You had one of each on your test. And by the way, each of those could have been done two different ways. So depending on how you started, if you sent a cosine out there by itself, that would work. Or if you sent a sine out there by itself, that would also work. And the other one, you could either send a secant squared out there by itself, or you could send a secant tangent out there, and it would work either way. So that was purposeful, that you wouldn't try one way and then realize it was not going to work, and then you wasted all that time. Both methods worked on both problems. But you rejected that gift, some of you, apparently. Trig substitution, page 401. You will encounter first of all, how are trigonometric integrals different from trigonometric substitution? Well, when you encounter a trig substitution problem, there's no trig in it at all. So if you see sines and cosines or secants and tangents, this is not the method. So we're going to actually introduce trig into the problem to try to make it look a little simpler. So there's no trig originally in the problem. You're going to see some square roots in the integrand, and they'll be of three types. Some number, when you see a, that's a number, and when you see a x, that's obviously a variable. It might not be just x, it might be 3x, the quantity squared, or something else. But so number squared minus variable squared, that'll be one type of radical we're going to see in the integrand. Number squared plus variable quantity squared. So you're not seeing any trig yet. You're not going to see it in the original problem. And then variable squared minus number squared. So all of them will have a square root. At least that will get us started in the fact that we have a square root in the integral, in the integrand. And we've got to make a trig substitution so that we no longer have a square root. So here's the substitution in the first one. We're going to sub in, wherever we see an x, we're going to plug in a, whatever a is in that particular problem. We're going to do an example, at least one example of each type. But whatever number a is, a sine theta. When we do that, we'll also have to find dx. I'll forego that for right now. When you see a squared plus x squared, or number squared plus variable squared underneath the radical, you're going to let x equal a tangent, and you'll see why these work when we go through example problems. Then we'll also have to find dx because it is a substitution. Obviously, the substitution involves trig. And in the last one, if you have variable squared minus number squared, you're going to sub in for every x that you see, you're going to sub in a secant theta. And again, you'll have to find dx. Let's go ahead and do the dx's. if x is equal to a sine theta, a is a number, derivative of x is a, because a is the coefficient. Derivative of sine is cosine theta d theta. So we're changing it from an x dx problem to a theta d theta problem. Here again, a is a coefficient. Derivative of tangent is secant squared. So again, changing it from an x dx problem to a theta d theta problem. If x equals a secant, a is a coefficient, we'll bring that along. Derivative of secant is secant theta, tangent theta, d theta. Now that right now is just a bunch of letters and trig functions. Let's see why it works. So let's take this one. So we're handed some integral problem, and it's got one of these in it. Number squared minus x squared. We're going to do another example beyond this, but here's why this substitution is going to work. So for x, we're going to plug in a sine theta, and it's supposed to dispense with the radical. So if it works correctly, we're going to have the square root of something squared, and the square root of something squared is that something. So that's kind of the goal of all of the trig substitution. So what's it going to look like? A squared has been untouched. For x, we're going to replace it with a sine theta. Now I realize we're also going to have to put dx in this problem. That's extra baggage, but I just want to go through enough so that you see why this substitution has a chance of working. So a sine theta squared is a squared sine squared. What can be done with that? A squared can be factored out of these two terms under the radical, and it leaves what? 1 minus. And what can be replaced for 1 minus sine squared? Cosine squared. So do we have the square root of a perfect square?
Yes.
What's the square root of a squared times cosine squared?
A times cosine.
A times cosine. So that's kind of why the substitution is going to be made, is that we're going to end up with the square root of a perfect square. What we did not do in this problem, that we have to remember to do when we get a real integral problem, is also incorporate dx, which is a cosine theta d theta. So we didn't do that, and that will become part of an example problem when we get there. So this thing that looks like the square root of something that's not a perfect square, with that substitution, it is the square root of a perfect square. And that's the reason why this has a chance of working. All right, the second one. If we have the sum of number squared plus variable squared under the radical. So where we see the variable quantity that's being squared, in this case it's x, we're going to plug in a tangent theta, and in a real integral problem we're also going to have to contend with dx. But let's see why this has a chance of working. A squared is left alone. For x squared, we're going to plug in a tangent theta, the quantity squared. We got to square the a and square the tangent. Very similarly, what can be done under the radical? Factor out an a squared. A squared as a factor, we can take the square root of a squared, and we're hoping that the rest of this is also a perfect square, what is the same thing as 1 plus tangent squared? Secant squared. So now you do have the square root of a perfect square. So the answer is, at least to the radical portion of this problem, is a secant theta. Is that all right? So we had seemingly the square root of the sum of two squares, which you cannot take the square root of that, but with the trig substitution it does change things, and we can. This will, when we're doing a real problem, this will actually kind of, even though this is simpler, this is going to make things worse. So we're hoping that the simplicity of this outweighs the fact that this is going to make it more complicated. Because we got to throw that in there for dx. So hopefully there's a net gain, hopefully, by the square root of the perfect square. All right, the third one is variable squared minus number squared. So you know why this substitution is going to take place. It's going to make, hopefully, this thing that is not a perfect square, it will make it a perfect square. So for x, we're going to plug in a secant theta. We're going to square a secant theta because we're squaring x. So that's a squared secant squared. They both have an a squared. You can see why the a is necessary in each one, because it gives us a squared in the first term, a squared in the second term. We can factor that out. Still doesn't look like the square root of a perfect square, but what is the same thing as secant squared minus 1? Tangent squared. So the square root of a squared tangent squared would be a tangent. So that makes the radical portion of the problem simpler, and hopefully it outweighs the fact that we've got to now replace dx with a secant theta, tangent theta, d theta. Sometimes it doesn't, unfortunately, that we kind of make it better here, and this makes it worse, and it's about the same as what we started with. But hopefully a doable integrand. So those are the three substitutions. Let's look at examples. This one is from your book. I don't believe it's an example in... It is. I'm not going to do it. It isn't. But it's one of the problems at the end of section 5.7. And I'll take the same approach that your authors are taking on these problems. I realize you have a boatload of stuff to memorize. Let me see where this is. This is problem number 10 on page 404. There are other problems while I'm talking about this. These are some good problems to look at to make sure that you know how to do. So on page 404, here are some trig substitution problems. Are there any web-assigned problems
I think so.
that cause you to use trig substitution?
I think so.
Okay. If there are and they cause you some difficulty, then we can talk about those tomorrow. But here are some good problems in the book. This is problem 10. So there's the giveaway right here, that we're going to use some kind of trig substitution, and based on the three types that we looked at, this would have been the third one, right? We've got variable squared minus number squared. Now in your book, the author says use the substitution x equals secant theta, okay? So all do the same thing. So I'll suggest the substitution. You don't have to have that memorized, but you do need to know what to do from that point. So if we use the format that I set up, we would say A secant theta, and what is A? A is 1. So you don't have to know the first step. I'm going to give you the substitution, but you have to be able to take it from there. Does that sound like a fair deal?
Yeah.
I know there's a lot of stuff to memorize here. All right, so let's go ahead and get this out of the way initially, because we're going to have to throw that in pretty quickly into the problem, because it goes right there for dx. And if x equals secant theta, what is dx? Secant theta, tangent theta, d theta. So with the substitution, let's see what this will look like. For x, everywhere we see an x, we're going to plug in secant theta. So it's supposed to help the radical. Hopefully it won't mess things up everywhere else. So x squared would be secant squared theta minus 1. That's going to be quick and easy. Down here, unfortunately, we've got an x to the 4th. So for every x, we're going to plug in secant theta. So that becomes secant to the 4th of theta. And now this is the first time for this. We've also got dx in the integrand, and everywhere we see a dx, we've got to plug in that whole mess. So hopefully, by simplifying the radical, we'll make this a workable problem. It's not guaranteed that it's going to work. It kind of depends on everything that's occupying space in the integrand if it's going to work. So what are we going to put in for secant squared minus 1?
Tangent theta.
Tangent squared. Is it like really hot in here?
Yes.
It's hot in here. Kelly, see if we can prop the door open or something. I don't know if that'll help, but something's got to counter the hot air that I'm putting out too. All right, square root of tangent squared in the numerator is
Tangent theta.
tangent. And then we've also got a secant and a tangent and a d theta. All that's in the numerator. And then we've got a secant to the 4th in the denominator. So no more radicals. That's the plus. Now, is it going to be better? That's kind of yet to be seen here. Any obvious simplifications?
Secant.
Secant, we've got one of them in the numerator. It's all multiplied, so everything multiplied and or divided. So we can reduce things. So one of these secants is going to knock out one of those. So we've got what? Tangent squared
Mm-hmm. Secant to the
over
third.
secant cubed.
Yes.
And then we've got a d theta. There's probably lots of different ways from this point that we can do the problem. If you don't particularly like secants and tangents, and you'd much rather work in sines and cosines, you could change the whole problem at this point to sines and cosines. I don't know, let's do that first, and we'll take another approach on the next example. So tangent squared,
Sine over cosine.
okay, sine squared over cosine squared. And that's divided by, I'm going to go ahead and keep that in here. What is secant cubed in terms of sine and cosine? Secant is 1 over cosine, right? So we have secant cubed, so that's 1 over cosine cubed.
Yes.
So we've got a complex fraction. Let's take care of that by multiplying by the reciprocal of the denominator. Does that help? cosine squared, numerator and denominator. So we've got a cosine squared. Here we've got a cosine cubed, so that will leave a cosine. Now that is something we've already done. That's trigonometric integrals, right? If we let u equal sine, derivative of sine is cosine. So this would be
U squared.
u squared. Now we're making another substitution. We got all kinds of substitutions going. We're going to have to kind of track them back when we're done. This is u squared, so u is equal to sine. And this is du, right? Derivative of sine is cosine. So this is u squared du, which integrates to u cubed over 3. And what did u represent temporarily?
Sine.
Sine. Now we're not done because we didn't start with a theta problem, so we don't need to end with a theta answer. We go back to our original substitution. X equals secant theta. I'll make a diagram of that. So there's theta, secant. So I want to, from this angle, label the secant of theta as x, or x over 1. Maybe you don't like secant, maybe you like cosine. Well, if the secant of theta is x, what's the cosine of theta? 1 over x, so cosine would be 1 over x. Is that right?
Yes.
So is this diagram correct for this statement?
Yes.
If I took the secant of this angle, would I get x over 1?
Yeah.
That's correct. And then if you have two sides of a right triangle, we can figure out the third. What's the third? Square root of x squared minus 1. Now, how are you going to know that that is probably right? Because look at the radical you had in the original problem. It has a square root of x squared minus 1 in it. So that's probably correct. We're going to replicate that in our triangle somehow. All right, so we have sine of theta cubed over 3. There's our answer thus far. And here's our diagram. So what can we replace for sine of theta?
Opposite over adjacent.
Opposite over
hypotenuse.
hypotenuse?
Yes.
So from this diagram, sine of theta is opposite over hypotenuse, and that's what we will replace for sine of theta. So sine of theta gets replaced by this. That was cubed in our answer. We divide that by 3, sine theta cubed over 3 plus c, so we replace that. So if it seems like there are multiple substitutions, you're right, there are. So one of them was kind of, we got into that substitution, the u substitution, and out of it real quickly. This one takes a little more work to get kind of out from under the theta, original theta substitution. So at least we did the substitution and it made the problem workable. Not saying that it's easy, but it is workable. Any piece of that question, that situation that you want to look at again? Yes, Blair.
Substitution where we use the u squared and du.
Okay.
For just a second.
So I kind of shortcutted that since we've done that already prior to Thanksgiving. We've got powers of sine, and as long as everything else is the derivative of sine, then we're in business. So we're really technically letting u equal sine du if it's going to help the cause. Has also got to be there, which it is. So if u is equal to sine, that becomes u squared. And if u is equal to sine, that becomes du. So that's u squared du, which is u cubed over 3.
Okay.
Anything else on that one? All right, next example. Again, the methodology of what we're going to do. You don't have to have the first step memorized, but you have to know what to do from that point. So this is the part you don't need to know, but somebody check what we've done since the start of class today. What should we let x be on this problem?
A tangent theta.
Okay, and what is a? 2. So let x equal 2 tangent theta. That'll be given to you. We also have a dx in the integrand. We're going to have to get rid of that. And what is dx going to be replaced with?
2 secant.
Derivative of
Squared
tangent is
theta.
secant squared. Is that right?
Mm-hmm.
All right, so what does that look like? Let's see. 1. Down here we've got 4 plus 2 tangent theta squared. And up here we've got to replace dx with 2 secant squared theta d theta. So the first step, if you've got x's and thetas, you're not quite done yet with that first step. You need to have no x's at all and thetas and d thetas after the original trig substitution. Does that look right?
Mm-hmm.
The next step, we'll know if this is going to work. So down here we're going to have 4 plus 4 tangent squared. I don't know if that looks like it's going to work to you, but if we factor a 4 out,
2 secant theta.
we've got 1 plus tangent squared. And 1 plus tangent squared is
2
secant squared, right?
Yes.
All right, let's go ahead and take the square root. Should be a perfect square in the denominator.
2 secant theta.
2
Yes.
secant theta.
Elimination.
This is actually going to work out pretty nicely.
Integrate secant.
So the
theta.
2's knock out. One of these secants will knock out with this one, right? So we're left with just a secant. I was hoping we'd have a secant in the denominator. That'd be nice because a secant in the denominator is really a what? A cosine? That would have been easier. Of those two, this is the most stubborn. But I think we did this one. This one is the one that had a little trick to it, where you had to multiply the numerator and denominator by secant plus tangent.
I don't remember.
We've done this before. You have to multiply numerator by secant plus tangent and the denominator. And that turns out to be, the denominator is u, and the numerator is du. So it turns out to be a du over u problem. So you can look back at your notes. We have done this problem before. Integral of secant is natural log of secant plus tangent. We're not done because our answer still has thetas in it. And what did we start with? We started with x's. So here's theta. What do we know about theta? We know the tangent of theta is what? X over 2?
Mm-hmm.
So how do I label this triangle so I can get rid of thetas in my final answer? If the tangent of theta is x over 2. Opposite is
over
x.
adjacent.
Adjacent is 2.
Yes.
Now we're probably going to know if this substitution is correct. What would the hypotenuse be? Do you see that in the original problem?
Mm-hmm.
So the fact that we see that same radical that we had in the original problem is probably a good sign. And we want to replace what?
Tangent and secant.
We need secant and tangent because our answer is so from that diagram, what is the secant of theta?
Square root of 4 plus x squared over 2.
Yes. And tangent of theta?
X over 2.
X over 2. So the worst thing about that problem is that we had to integrate the secant of theta. Questions about any part of that one? All right. So we have not seen an example of what type. Make sure we get that.
Number 1.
We did.
Mm-hmm.
A squared minus x squared.
We need an a squared minus x squared. Okay.
What's this one?
So there's one of those radicals again. Again, this part would be given to you. Let x equal, you can probably figure it out from what we started class with, 2 sine.
Yes.
So from this point, you need to be able to take it from here to a final solution. So derivative of x is 2 cosine theta d theta. For x down here, we've got x squared, so that becomes
2 sine squared.
2 sine theta. Square that product. Under the radical, or minus x squared. So that's all denominator. And in the numerator, we've got a 1, which I already have, and also a dx. So a quick check to make sure we've gotten rid of all the x's and we have either thetas or d thetas, which is the case. So we've got 2 cosine theta d theta. Here we've got 4 sine squared. That's kind of irrelevant to whether or not this is going to help us solve the problem. Here's the relevant piece. Are we going to be able to get rid of the radical? Well, that becomes 4 minus 4 sine squared. And let's see if we can put a couple steps together. We can factor out a 4 under the radical. And that leaves us with what? 4 times 1 minus sine squared. And what's 1 minus sine squared?
Cosine theta.
Cosine squared. And what's the square root of 4 cosine squared? 2 cosine theta. All right, so that's what's supposed to make this a doable problem. Yet to be seen, but now we kind of start looking at like terms, numerator and denominator. What leaves us?
2 cosine.
Okay, 2 cosine theta. This is actually division by 4, right? So we could bring that out front as 1/4.
Yes.
That's a 1 d theta, taking care of the 4. Yeah, this is going to work pretty nicely, actually, better than the one before. What is the same thing as 1 over sine squared? Reciprocal now. It would be cosecant, right?
Would it be better to leave it in sine? Since x is
I think
equal-
it's better in this
Yeah.
case, and that's really, you'll see, I think, in this next answer. Is that the derivative of something? It's pretty close. Now, you're probably used to derivative of tangent is secant squared. What's derivative of cotangent?
Cosecant.
Cosecant squared. So it's pretty close. If we put a negative here and a negative here, we're in business. This inside the radical is the derivative of cotangent, so the integral of the derivative of cotangent ought to be cotangent. What's left in this problem?
Replace
Okay, we got to get rid of theta, and probably we'll get rid of cotangent theta in terms of x. So from our original substitution, what did we substitute? X equals 2 sine theta, so x over 2 equals sine theta. How do I label that triangle?
Opposite is x.
Opposite is x.
Hypotenuse is 2.
Hypotenuse is 2. And then if we know two sides of the right triangle, we can use Pythagorean theorem to find the third. What is the third?
4 minus x squared.
Hypotenuse squared minus leg squared, square root. You see that same integral, that same radical in the original problem. It's there. Probably means we're accurate. And we want cotangent theta. Well, tangent would be opposite over adjacent, so we must want adjacent over opposite. There's adjacent, there's opposite, plus C. Does that work? So you're going to be expected to, I'm trying to wait till you're done writing, solve this problem, and you're going to be given that statement right there. In fact, on all three types, you're going to be given the first step. Okay, we did one like that. So we've done one of each type. Is that correct? All right. Once again, take a look at these problems. I think we did 10. already in your book, and that'll give you a sample of what to expect from trig substitution. There's no trig in the original problem. There's some ugly radicals that have either sums or differences under them, and that's the task, is to get that simplified. Questions? We are done. Literally done. I feel like we've been cooking for 50 minutes.